Hi everyone. In this video, I want to explain how you can set up a synthetic aperture radar simulation in HFSS so you can do some imaging quote unquote experiments. So what we'll do is we'll start off with the horn antenna design that you had for your antenna pre-lab. It's just a simple horn antenna. You'll have to modify a few things to be able to use it for the SAR simulation. Okay, so I'm going to set up a simple SAR simulation here using a new tool in HFSS called SBR Plus. Although you can do it with other simulation setups like physical optics or integral equation. There are many tutorials on that, I think, online, whereas SBR Plus is relatively new and very powerful, very fast, really good for imaging type setups. So to use SBR Plus, what you need to do is open the antenna design that you had and we'll change a few things. So the first thing you need to change is go to HFSS solution type and make it hybrid. Okay, and the next thing is that change the aperture so that you have about 60 degrees of beam width, and you solved this in your pre-lab, hopefully. So I think the aperture width should be 30.8 millimeters, and the height should be around 23.8. If you can use the numbers that you got for your pre-lab from the antenna experiment. Okay, and then you also found where the phase center is, and we'll set up a coordinate system with the phase center, with that phase center. So for that, hit modeler, coordinate system, create relative offset, and then I'm making it 0, 0, -1. I think the phase center is around somewhere here. And then you can rename this to phase center coordinate system. Okay. So once you've done that, the next thing we need to do is we need to make sure it recognizes this phase center. So right click excitations and hit select phase center, and then hit select the PCCS as the phase center. Okay, so you've done that. So now the boundary is done, the excitation is done, and you also set the phase center coordinate system. The next thing we need to do is modify the analysis so that as let's say 51 points. That should be enough for the imaging that we need to do right now. But keep in mind that the number of points determines your aliasing free range. So if you have targets that are further out, or if you have some reflections that can get aliased into your target range, you may want to use more points. But in this case, since it's a simulation software, there aren't really any targets beyond our target of interest. So I'm just using 51 points. The next thing is you need to set this to a discrete sweep. It needs all the frequencies in discrete sweep to be able to solve SBR. So by SBR is shooting and bouncing rays. You'll see it when I set it up. I didn't mention that, I think. So anyway, so set this, hit OK, and that should be it. You can hit validate, close, and analyze. It should take just a few seconds. Once it's done, we'll continue. Okay, that took about a couple of minutes, and simulation is done. So now we can go ahead and set up the rest of the stuff. So we need to set up a target. In this case, I'll be using a corner reflector because it works really well with geometrical optics. So for this, what you need to do is hit project, hit insert HFSS design. We need to use HBR plus. So change the solution type to SBR plus. And then I already made a target, so I'll just import that here. Hit modeler import, and I'll upload this this file. So I need to go to Dropbox courses. Okay, this one. So I'll upload this file into Canvas. You can use this one. Hit open, and that should import these corner reflectors. Okay. So what you need to do is that this is just a model file. It's a step file. So you need to assign a boundary to these corner reflectors. So for that, just hit the 4 rectangles, hit right click, and then say assign boundary perfectly. And then you can just use the defaults. So then it's assigned a perfect electric conductor. You can assign different boundaries. You can assign a finite conductivity or any other impedance boundary. Okay, so the corner reflectors are ready now. We can rename this to 4 square. Then moving on, we want to set up the actual design file, the simulation file where the whole thing takes place. So insert another HFSS design. You can rename this to main, if you like. Again, we'll use SBR plus. All right. So before we import our antenna and the targets, we need to set up a couple of coordinate systems. So hit modeler, coordinate system, create, and then you can just say offset. So this will be the target coordinate system. It would be at 0, 0, and we call it Z target. And we'll make Z target 0.5 meters. I've said meters, not meters. 0.5 meters. Okay. And the next coordinate system will be, so let me actually rename this. So I'll call this target CS. Okay. Next coordinate system will be our antenna coordinate system relative. We'll just say offset. So I want to actually just set this to 0. It's better to change it like this for some reason. It understands units better, I guess, but hit relative double click here and then set this to X offset, Y offset, and 0. So then we set X offset to be NX times lambda over 2, where NX for now would be, let's say, 1, and lambda is C over F, right? Hit enter, and then you set C to 299.792.458. And we hit F is the frequency. So you will select the largest frequency in this case, which is 12 E9, 12 gigahertz. And then Y offset is NY times lambda over 2, and NY also I'll set to 1. Okay, so that should set up the second coordinate system. We'll call this the target coordinate, or not target, sorry, the radar coordinate system, or you can call it the phase center coordinate system. So now we have both coordinate systems ready. Let's import the target. So you first click on target CS, say draw 3D component, browse, and import the model that you exported. Now I actually can't remember if we exported it. Okay, maybe we did not. So the way to export it is to select everything. You can either hit O and then select everything, or just hit this. But let's say we'll just click all these 4, and we need to export it first. Sorry, I forgot about that. Hit 3D component library, create 3D component, hit OK. And then I already saved it earlier because I was kind of trying this out. You can save it at that as the same thing, and hit save. Okay, so then we go back here and we import it. So draw 3D component, browse, and then we import this one. And then you can select here which coordinate system to import it into. Okay. So now it's imported into this coordinate system. We go to our radar coordinate system. Why is this all the way out here? The reference for all the coordinates should be global. Yes. It's not, this looks right. Just make sure the reference is the same. Okay. So one thing we need to do is we need to flip the corner reflector so that they're actually facing the target. There are many ways to do this. One way, I'll just show you a couple. You can just hit O for object, select all, right click, and you want to rotate them. So before rotating, one thing you can do is change the coordinate system to the target coordinate system. Then select all, edit, arrange. Why is it not allowing me? Okay. Hit that, change, rotate. Okay. And then hit X, and then you can set this to 180. So that should rotate everything. But the way I did it is that this guy came on the bottom now. You can also rotate it in y-axis, so then it'll look symmetric. But another way to do it is to rotate the coordinate system itself. So the way to do that is to go to target coordinate system, and then you can select axis position. This is the position, and you can change the axis to be -100. So now basically the x-axis is pointed in the direction of -1 with respect to the global coordinate system. Okay, so now it's facing the target, it's facing the radar. So next we import our antenna design into this model. So select radar CS, open it up, hit right click, and then say create antenna. So here you can create different types of antennas that are already present in HFSS. This is actually somewhat easier. You can also create a parametric beam so that you can just set what the beam widths you want are, what the polarization is, what the footprint size is. This is the aperture area of the radar system of the antenna, and also the impedance. This is also faster, but in this case, I just wanted to be more realistic. So I had you create an antenna. So to do that, to import that, you hit create antenna and then say link to source design file, set up a link, say use this project, choose your antenna, select sweep, and then simulate the design as needed. Make sure all these are fine, and then for the visualization, you can use the horn, the object, and the port cap. I'm not visualizing the radiation surface because that you can't see anything inside if you do that. It's just a weird bug right now. Okay. And then you can use the far field. This is faster than near field, although near field is more accurate. So you just go with the far field for this one. Hit next and then hit finish. So that should import your antenna into this design file. Okay. So then if you look at the excitation, you see that it's using the whole box as an excitation for this design. That's pretty much it in terms of setting up things. What I'll do is go ahead and run a simulation. Actually, yeah, sorry, I need to set up, first I need to set up a simulation, right? So for setting up, you can choose from 8 to 12 gigahertz, and then you can say linear count 51. Just use the same settings as you used in the original file. You don't need to compute the fields, we just want the S parameters. So you can set these as defaults, but these basically enable you to improve the accuracy of the simulation. You can use creeping waves if you have round objects, for example, and diffraction corrections if you have sharp edges that you want to account for. These do work well, but if you want really high precision stuff, then you probably want to use either physical optics or method of movements instead, which is somewhat faster than this, slower than this, but more accurate. But since here we are using corner reflectors, geometrical optics is very accurate with corner reflectors. So we can just go ahead and then hit OK. So that should be it. I'll run a simulation and it should take just a couple of minutes. Once it's done, we can continue. Okay, one thing that I actually did forget before I ran the simulation is that this is sort of weird. I don't know why it's set up this way, but you need to hit right click excitations, select TX/RX and hit this, make sure this is green. So this will actually save the S parameters correctly. Basically, it will assign this antenna as a transmitter and a receiver. It should be default on, but it's default off. And if you have multiple antennas, you can select which paths you want, like S21, S31, S32, and so on. You can also use this for modes. So this is basically saying antenna 1, port 1, mode 1, port 2, mode 2, I think. And if you have multiple modes and you want to see how different modes interact within the same antenna, if you have a multimodal antenna, for example, then you can set that as well here. So let me actually just hit this and then let me clear all these messages and then we'll run the simulation again. Actually, before I run it, I can show you what the results look like if you don't have that. So we'll plot S11 in dB and you should see nothing. Let's run it again. Okay, once the simulation ran, after that correction, it actually ran almost instantly because it had already solved for the fields, I think, or the S11, but it wasn't displaying it. Anyway, so now we have this for the S11. You see that there's a slowly varying frequency. Slowly varying curve, I guess, because this is in frequency, and then also a fastly varying curve. That's what you should expect because the fast one comes from the reflection from the target. Okay. Now what we want to do is that we want to run a parametric simulation so that we take the same S11 data for different positions of the antenna. That's how you create a synthetic aperture. So for example, in this case, if I go to 0, 0, and that goes there. And let's say I want to do make an aperture that's around 5 lambda by 5 lambda. So you can orient this to be in like this. So if I want 5 lambda by 5 lambda, since I've set the step size to be lambda over 2, I need to go from nx equal to 10 to minus 10, right? So I'm just checking now if it covers the whole area sort of, and this looks pretty good. Yeah. So I'm just making sure that the 4 corners cover the area of the targets. That's not really necessary. I mean, because in this case, we'll be using a algorithm called back projection. Back projection doesn't really care about that, but it is important because you want to make sure that the beam is illuminating all the targets, no matter where the antenna is. That's why we want a beam width that's very broad so that all targets fall within the beam when you're taking an image, when you're collecting the data. Okay, so we can go ahead and run a parametric simulation that collects S11 for all positions on an XY grid of 5 plus or minus 5 lambda. So that's around 10 lambda in X and 10 lambda in Y. So that's 20 by 20, so 400 simulations. And that's why you're using SBR, because SBR just takes about 20 seconds or so per simulation. So it should take a couple of hours to finish. Okay, so the way you can set that up is you can either use Optimetrics. So you can say add parametric and then say add, let's say you want to set an X from minus 10 to 10, and make a step of 1, and then hit add, and then and Y also minus 10 to 10 and add, okay, and then hit okay. And then to save as parameters, one way to do it is to go to design settings, export on completion, and then export to a sum folder. So this is sort of the easiest way, but it's not very versatile. And I just want to use this as an excuse maybe to show you a different way, which is, I think, much better in terms of what you can really do. So the other way to do it, so let me just get rid of this, delete. So we'll use scripting. This is a nice place to show you how scripting works. So the way scripting can be done is that you can use a Python file to tell HFSS what to do. And HFSS makes it really easy to do that by letting you record a set of actions into a script. So let me show you how to do that. So what you want to do with this is that, say tools, record script to file, and then just say start script, for example. Okay, so now every action that I do now will be recorded into a script. So the first action I want to do, for example, is click here and then say nx equal to 0 and y equal to 0. Okay, so now I've gone there. Then I hit simulation, validate, close, analyze. Now it's going to run a simulation. Once it's done, I'll come back. There's one thing that I wanted to change before I actually recorded the script. So let me do that again. So what we want to do is we want to create a S11 file. Let me say real, add imaginary, close. Sure that we export this. So I'll call this S11 complex. Okay, so now I'll record the script again. Record script to file, start script, replace it. So you want to set this to, let's say, 1 and y to 1. And we also want to run the simulation once. So validate, close, analyze. Should be done pretty quickly because we already simulated this one. Okay, done. And then I want to export this. So you need to be careful which operations you run when you are basically exporting some file. or when you're recording a set of actions to script. So just be careful. And then I'll just say save. And then I want to stop script recording. Okay, so now let's take a look at what the script has recorded. So, okay, so it said, okay, set the active project, set the active design, and then it changed the variable nx to 1. And it also changed the variable ny to 1. And then it saved the file. It ran the module, ran the file, the simulation, and then it got the report S11 complex, and then saved it in this location. So now we'll modify this script by adding 2 for loops. And the for loops, what they'll do is they'll run through all the different positions of the antenna over an XY grid and save the S11 files from all of those positions into basically all of these S11 files. So for each position, you'll have an S11 measurement. Scripting is really powerful because it can help you do a lot of other things. I mean, if you want to say, for example, the fields on this boundary or this space, you can also save that using scripting. So it's very powerful. That's why I wanted to show you this different approach. You can also run optimizations routines because now you have access to a Python code, right? So you can say, if you run the simulation, get this variable, set up a cast function, and use libraries that have optimization routines. You can also use MATLAB to control or modify the Python script that controls HFSS. So you can have that environment as well. Okay, we want to modify this script so that we have 2 for loops that run through nx and ny and save those files. So let me just set that up and then I'll continue. Okay, so all I did here was I added in 2 for loops, and then I changed the value of nx to basically take the value in the for loops, and the same for ny, and also for the file that you export. So I changed that file name to S11 complex nx and ny. Okay, so what you can do is once you modify the script, go into HFSS and then say tools, run script, and then select that script. So now it will basically loop through all the values. So it's going to basically solve for this location and then change it to a new location, solve for that, change to a new location, find that, and then keep doing that. This will take some time, maybe a couple of hours, because there are just so many data points, about 21 by 21. So that's over 100 points. And that's why probably you don't have to run this. I'll actually run this for you and then save the data and then upload it to Canvas. So you can just use the measurements for your SAR processing. So I'm just going to stop this. Okay, so now let's go to MATLAB. What you should have is basically a set of data. I'm just going to delete this one. Set of data, S11 data for all those measurements that you just did, all the huge simulations that you ran. So I have a code here that consolidates all of those measurements into a single data, into a single variable. It's pretty simple, the code. One thing I should mention is that when running this simulation, I use slightly different parameters. So I set the number of points to be 401 points. And I also set the center frequency to be 10 gigahertz, even though the start and stop is 8 to 12. So which means that, like, go back here, I set this to be 10E9. So that calculates the grid points a little differently, because now the step is determined by a lambda, which is slightly larger, about 3 centimeters or so. Okay, so I basically set these values and I ran nx from -10 to +10 and ny from -10 to +10. So that's 21 by 21 grid. So I basically run through all those files using 2 for loops, and I save it into a single 3-dimensional S11 variable. So if we run this, it should say, yeah, this one, S11 3D. The first dimension is the frequency, second dimension is x-axis, and third dimension is y-axis, right? So if I open it up, you can see what it looks like. So yeah, these are all the frequencies and all the S parameters, complex values, right? So then I save this into a MATLAB file like this, S11 3D SAR S-4. I'll actually upload this one. to canvas, so you can use this for your SAR processing. So let me actually show you how to do that, since it's maybe a bit too much work for one pre-lab to have you to write a code. So I'll just write the code for you and show you how to do that. So once I do that, I'll resume again. Okay, so this is what the code looks like. Let me just quickly run you through the code. We start by, so let's clear everything. You start by loading the S parameter file that we just saved. And then we just change basically the dimensions so that the first two dimensions are X and Y and the last dimension is frequency. It's just somewhat easier to do it this way. And then you set some basic parameters, the number of frequency points, the range, the range resolution, the aliasing free range, and so on. And then you define the grid points that we set up in HFSS. So we go from -5 lambda to 5 lambda with a step of lambda over 2. So that should give you 21 points by 21 points. And then here I'm setting up the back projection algorithm. So this is the simplest form of simplest and also the most general way to do imaging. The basic idea behind back projection is that you have all these grid points on which you collected data, right? So there is a signal that started at your antenna. It went through space up to some certain pixel distance and then hit the target and came back, right? So the way back projection works is that it sort of unwraps that phase from all the antenna locations to each pixel location and then adds them up. That's a very simple explanation. I mean, you'll have to really go through the math. And this algorithm is covered in the lecture notes, so you can look at it. The equations are there under the inverse synthetic aperture radar section, but the basic idea is the same, is that at each pixel, you basically unwrap the phase from each antenna location and add them all up. So what that does is that if there was actually a target in that location, when the phases get unwrapped, they all add up coherently. Whereas if there was no target at that pixel, then the phase does not add coherently and you don't see anything there. Okay, so the implementation of that is inside this function. Okay, so the implementation of back projection is inside this function where I'm sending the S11 data, the positions of my antennas, the frequency range that I've used, and the imaging domain. So the pixels basically, at which I want to create an image. So here I've set the distance of the target to be 1.1375. Actually, in the simulation for this data that I'm using here, the target location is actually 1 meter. So I've placed the target at about a distance of 1 meter when I collected this data. But the distance that I'm measuring at or I'm imaging at is a little bit more than that, because 1 meter is with respect to this phase center here, whereas S11 starts from the back of the antenna, right? So it takes some time to go propagate and come back. So this extra length makes it that gives it this 1.1375 factor. So anyway, that's the range at which I'm forming an image. So let's look at quickly how I've implemented back projection. It's a very simple code. One way to do it is to write 5 for loops where you basically loop through all these 5 variables and then coherently sum up the phase. But here I've done it a little bit differently, where I'm using a vectorized approach where I have 3 for loops where I run through basically each position of the antenna. So for X position, Y position, and each frequency, I find what the phase compensation that I need to use is. And then I multiply that with the measured S11 data. So to basically unwrap all the phases for each antenna at a given, for a given antenna and for a given frequency at all the pixels that I'm imaging, I unwrap the phase. And then in the next instance, I go ahead and unwrap the phase for the next antenna, and then I add it up to the previous pixels. So this is one way to do it. Alternatively, you can also vectorize the frequency, X position and Y position, and then for each pixel, you can add up the compensated S11 measurements. That may seem kind of confusing if you don't really understand what the back projection algorithm is doing, and I don't want to use this video to explain it. You should hopefully understand it from the lecture notes and from the lecture. So this is just to provide some assistance in getting this done really quickly, because you may find this interesting and it's pretty useful, I think, in case you decide to do some imaging experiments in the future. I mean, it's useful or interesting anyway. So let's run this back projection algorithm, and let's see just for a single position. So I'm just forming an image, a 2D image really, but I can also form a 3D image. So let's see. So I'm running it. I need to run it from the beginning. So I run this section and then I run this section. Should take just a few seconds. Okay, so now we'll plot it. So I'm just plotting it at basically at that range. So Z in this one. I'm finding the maximum in the whole image and then I'm normalizing to that maximum. So I'm basically plotting it at this range, which is where we made the image. I create a 2D mesh grid of the 2D image, and then I find the magnitude in dB and I plot that. So let's look at what that looks like. So what we're expecting is to see basically something like this, right? Like with these targets, you should only see the face centers really, these 4 points. So let's see what we get. When I form an image, I see this. So this definitely does not look right. Something is wrong. And that is actually deliberate. I did make a small error in this code of the back projection implementation. And it is sort of your job to figure out where that small error is. It's a very small error, but it makes a big difference. So that's a hint. Okay, so what I'll do now is I'll quickly fix it and then come back, run the code again, and then show you what it looks like when it's correct. Okay, so now it's fixed, hopefully. Let's run it again. Okay, so now I ran the back projection algorithm. Let's take an image and there you go. So you see that you have your 4 targets, and this is sort of the point spread function of your imaging system. So you obviously don't have infinite resolution. You'll see something like this. And I'm plotting about 20 dB down. So you can see that there are some side lobes showing up and there are some other artifacts, but basically this is what you should expect. So, okay, that's pretty much it. You can actually plot a larger volume 3D image even, and then see what it looks like. It will take longer, but that's basically the idea of back projection. It's pretty simple. The drawback, though, one advantage of back projection is that you don't need to have a rectangular uniform grid on which you sample the backscattered fields. You can have any orientation. You can use it for MIMO. You can use it for many, many different scenarios. It's very general, but the disadvantage is that it is slow. It takes a long time because you basically have to compute. Even with this vectorized approach, it takes a long time because you have to compute 5 summations basically. So it's quite slow. But if there are other algorithms that you can use to make things faster, but for this demonstration, I think this is pretty good. So what I'll do is I will upload onto Canvas this file that you can use, so you don't have to generate all these using HFSS. I will also upload the step file for the 4 corners, and I will upload you can use the same file that you had for your pre-lab. So I will not be uploading this radar pre-lab 533, the one that I've just modified. You can go through and modify it yourself from the steps that I show you in this video. And I'll upload obviously this code, and I'll upload the wrong version of the back projection algorithm, the one with the small error. And hopefully you can fix that small error and get the image that I just showed you. And I'll actually also upload one more S11 file just like this with an image of a target that is unknown. So you need to take the image, form the image and see what that target is. And hopefully you find that somewhat amusing. Okay, thank you. Good luck with the pre-lab. I know it was kind of long, but you basically just have to go through the video and do everything that I did. It shouldn't take you more than an hour or two. All right, good luck. Thank you.